Hello, everyone. Thanks for coming my talk today. So my name is Juntao from Cornell University, and today I'm going to talk about the Anaphora resolution beyond the OntoNotes. So the recent years, like the reference resolution on the OntoNotes corpus has been dramatically improved. From the 2012, so the kernel F1 scores only have like 60.7, and then during the recent years, the performance has been dramatically improved to up to like 83.1 percentage point by using the contextual dependent contextual embeddings such as SpanBERT, BERT, or Elmo, and also benefit from the neural network. So we can also like the jointly using the things like the question answering and so on. So as a result, the performance has been improved to the 83.1. So around like 23 point difference like compared to 8 years ago. However, the OntoNotes corpus has a number of limitations. So it's only annotated very limited types of the reference resolution, majorly the single antecedent anaphoras. And whereas when compared to a corpus such as a RAW that has a rich, the anaphora types annotated, the OntoNotes corpus does not annotate the singletons, and it only annotates the predictive non-referring expressions, and with all different other types of the non-referring expressions unannotated. And it also does not annotate things like the split antecedent, bridging reference, and only annotated very limited the discourse diaxis as well. And as well as it does not annotate the ambiguity labels. So, which on the other hand, the raw corpus have everything annotated in this table. So in this work, we were majorly using the raw corpus and then trying to explore like all different anaphora resolution aspect. So which in today's talk I will cover 3 of our recent papers. The first one is called the class ranking module for full anaphora resolution, so which will cover our works on the singletons and non-referring expressions. And the second work is free the plural unrestricted split antecedent anaphora resolution. As the name suggests, it will mainly focus on the split antecedent anaphoras. And the third papers we will present today is called is our works on the bridging reference resolution. So let's first take a look at our first work. So our works on the singletons and the non-referring expressions. So this work is in collaboration in Alexandra and Massimo. So we will cover 3 tasks. So because of the singletons and non-referring expressions have a rich resource, so we can actually do it jointly with a single antecedent anaphoras, so in a joint fashions. So here we choose cluster ranking instead of the normal mention ranking plus architectures. It's mainly because a few different reasons. So the cluster ranking has a few different advantages when compared to the nowadays those mention ranking modules. So it's firstly it's linguistically more appealing, and then it also actually, so in our case, we show that the system is actually simpler than the previous mention ranking plus the entity level features modules, such as when compared to the Leotard 2018, the system has roughly 10 million parameters, whereas our cluster ranking system, we by directly link the mentions to the clusters, we only use like 5 million parameters, which is half of the size when compared to their systems. And one of the main reasons here for the non-referring expressions we use the class rankings because it's more flexible to handle the mentions. So such as we can do like the pre-filtering for the non-referring expressions once it's been identified. And also some potential like the advantages for the class ranking system is the first is it can explore more richer the class level features, and also it supports more advanced search algorithms such as beam search. So we leave those into the future work. So in this paper, we cover the first three advantages for the class ranking modules. So let's first take a look at what's the mention representations for our system. So we basically adopted from the Leotard 2018 system, and with one major changes, which is we replace the almond embeddings with the bird embeddings. As the later work shows that the bird embeddings actually improve the performance by quite a large margin. So basically, we concatenate the word and the character-based embeddings and bird embeddings, concatenate them together, and put it through a bidirectional LSTM, a multi-layer one. And after that, we create a weighted sum of the word representations in the mention as a head representation, and together with the start of the mention and end of the mention representations to form the mention representations. After we create the mention representations, we will use a mention score, just a simple fit for a new network. And then we will choose the same 0.4 mention per token, same as the Leotard system, to do some filterings about the mentions. And then after that, we attach our mentions directly to the clusters progressively. So to form the cluster representations, we use self-attention, in the for the mentions in the clusters, and then use a weighted sum as our cluster representations. So we also included, in addition to the mention representation, we also included a small feature called the positional embeddings to keep track on the positions of the mentions in the cluster. One another things we did, which shows to be very helpful for in terms of the performance, is the use of the cluster histories. So without the class histories, the normal class ranking system where add the mentions into the clusters directly. So such as the example here, we have the Steven Jobs, he, and Steve as one cluster. If we have another mentions, the Apple founder, we will add it directly to the clusters. But by doing this, we have some disadvantages because the most frequently, the most active, like the clusters, only have one forms of the representations there. So it decreases the chances of selecting the correct mentions. So that's why we include the cluster histories. So by cluster history, we mean, so if we have the clusters, the same class here, we will keep like the Steven Jobs as one cluster and Steven Jobs he as another cluster, and Steven Jobs he, Steve will be three like the cluster histories then compared to the one in the above examples. So if we add new mentions to the Steven Jobs clusters, we will create a new cluster representations here, Steven Jobs he, Steve, and the Apple founder. So we'll keep all the history clusters such as Steven Jobs he, Steve, and then so this increase the probabilities to give the more weights to the more active clusters. And in terms of the handling of the singletons and the non-referring expressions, so we extend those dummy scores used in the Leotard system to the different classes. We use one scores for the non-mention, and then one scores and one or many scores for non-referring expressions, and then one scores for the discourse new. So by adding the discourse new scores, in addition to the non-mention scores, so we've already naturally solved the singleton clusters. So which is cluster, which is the cluster have only one mention, and then it's discuss new mention. And for the non-referring, so all systems can be further extended to do the like the more fine-grained non-referring expression by just expand the second the non-referring scores to the multiple clusters. We can do that. And in terms of non-referring expression, as I mentioned before, so we were trying to fit it out once it identified by the classifier as a non-referring. So we call this a pre-filtering strategy. But this pre-filtering may be too harsh to sometimes get rid of, like the actually the discuss new mentions and so on. So we introduce a new hybrid rules which give a threshold. So if the non-referring expression mentions have a threshold like above, like let's say 0.5, then we will do the pre-filtering. Otherwise, we will do the post-filtering. So after we create all the clusters, and the remaining non-referring expressions will be added to the output. So in terms of the training, we use the same marginal log likelihood as used in the Leotard 2018 system, and we also introduced the trainings on the Oracle clusters, which means we use the gold cluster IDs to create the clusters, which is the Oracle cluster here. So by doing this, we significantly speed up the trainings. So if we train on the predicted clusters, so you need to do it like the one mention at a time. So it's a bit slower. So it takes like 80 hours to finish our training on a single GPU. And whereas if we use Oracle clusters, we can actually improve the speed by 5 times. So in the end, if we use the Oracle clusters, we only need like 16 hours, so which is much faster. So the first things we did is we evaluated our systems on the raw corpus. As we can see, so our systems outperformed by the previous those rule-based systems by quite large margins. So this Leotard system is a Stanford deterministic system, and by the way, so they use gold mentions, whereas in our case we use a predict dimension, but our performance is much higher than theirs. Even they use a gold mention, and we evaluated in the 2 different scenarios, which by include the singletons or the singleton excluded. By means the singleton excluded is just a normal the kernel evaluation, the kernel 2012 evaluation is similar to the OntoNotes evaluations, and we did additional experiment by using by training our system without the non-reference. And in a singleton excluded cases, as we can see here, so our system trained with the non-referring expressions always outperform the system trained without the non-referring. So actually, by identifying the non-referring expressions, it does improve the performance even for the reference chains. So, and we also report the scores for the non-referring expressions. As we can see here, our system achieved like 75.5 if you're doing the pre-filtering, and doing hybrid method, it does not drop much. And then if you do the fine-grained non-referring expressions, you get much better. So for the fine-grained non-referring expressions, we also try to identify the each individual types. As we can see, our system works exceptionally well on the expletives, achieved 100% recall and then 93.8 precision, so which is very good. And we also achieved quite reasonably good results on the predicates as well. And then the other classes, the performance is slightly lower. So although our system is not designed for the OntoNotes corpus, we also tested our systems on the OntoNotes corpus. As we can see from the tables, our system achieved the results equivalent to the Canton and Goberson. So their system is like the extensions of the Leota 2018 system and uses the BERT embeddings similar as ours. And they also a system like combines the mention ranking modules and then with the extensions to access to the entity level features. Whereas our system is much simpler, but yet we achieved a very competitive results than theirs. And we also did some analyze on our system. So the first things we did is we trying to say like the weights for the different positions, like the mention in the different positions. This is mainly because the discovery in the linguist that the first mentions which introduce an entity usually have a more the information such as so we will first introduce Stephen Jobs, and then later on we will refer it as a he or Jobs or and so on. So it will normally be a reduced form of the representations. So our system actually captured those the importance of the first dimensions of the cluster. As we can see here, by the different size of the the cluster size, and then the first dimensions of the cluster of our cluster always have a slightly higher weights when compared to the subsequent mentions. And the second thing we did is ablation study. So we're trying to understand the importance of the different parts of our system. So the first things we did is we remove the positional embedding, and this result 0.7 decrease. And the second, we remove the cluster-wide embeddings, and this result 0.4 decrease. And if we remove the cluster histories, we will lose like 1 percentage points. And the last experiment we did is we trying to train our systems on the predicted clusters, so without using the Oracle cluster. So as I mentioned before, so by using Oracle clusters, we already speed up the training, but it not only speed up the training, it also gain additional like the performance as well. So it improved by using the Oracle cluster, we improved the system by 0.6 percentage point. So this comes to our second paper on the split antecedent Anaphora solution. And this paper is in collaboration with Nafis, Silvio, and Massimo. So let's first take a look what is a split antecedent plurals. So we have like in terms of the plural mentions such as they, we will have like the few different cases. It can be like a singleton antecedent. So let's say the first two examples. If we have the antecedent such as the Jones went to the park, they had a good time. The Jones is antecedent of they, and it's a single antecedent plurals. And then we have the John and Mary, so it's connected by a coordinate conjunction. And then we can also represent it with a single antecedent as well. So John and Mary will be a one mention. But we have those harder cases that's the antecedent of a plural and of a plurals cannot be represented by the one mention, such as the example here. John met Mary in the park, so they had a good chat. So this example here, we will have the antecedent of they will be two mentions, John and Mary. And we also have the anaphoras, the split antecedent anaphoras beyond the pronouns. So we will also have the nominal nouns, such as those both colors here. The both color refers to green and blue. So this work is the works on the split antecedent anaphora is quite limited. We're only aware of like the two different systems, the modern system trying to solve the split antecedent, but they also restricted to some restrictions, such as the system only trying to solve the they pronouns, and our system is the first system trying to solve unrestricted split antecedent pronouns. So one of the major challenges of doing the split antecedent is the lack of the resource. So the largest corpus we found with unrestricted split antecedent annotated is the IRL corpus. Here we use all the subclass of the subcorpus of the IRL corpus, and then to form our training, development, and test set. So in total, we only found like 700 like the Anaphora split antecedent Anaphora examples, and then we split further into the training, development, and test set. So which, as a result, we only have 500 like examples for training. So in order to conquer the disadvantage, we introduce some auxiliary corpus. So we introduced two of the corpus. The first two corpus start with PD, is the corpus we created from the crowdsourcing corpus, the first detective crowdsourcing corpus, which has the split antecedent anaphoras also annotated, but annotated with noise using the crowd workers. And the third and the fourth corpus, we using the bridging anaphoras and also the single antecedent anaphoras, provided in the IRL corpus, so which has a bit larger, such as a single antecedent anaphoras has a much larger, the examples when compared to all the other cases. So let's first, so this is the first detective game. So it's also collected within the group in collaboration with Essex University. And we use the latest release of the corpus, the PD2 corpus, which can be downloaded from our GitHub page. So the corpus, because it's like the crowdly annotated, so in order to be used it as a normal like code annotated corpus, so it comes with some silver labels aggregated by a mention pair annotation module, aggregating method called the mention pair annotation module. And in total, the silver labels provided like around 500 split antecedent anaphoras. And with a recall of like 68.8% of the gold split antecedent anaphoras when we evaluated on a small portion of the gold annotated PD corpus. But if we look at the crowd annotations, we found much more like the mentions, the split antecedent annotations. So in total, we find like the nearly 50K splitted antecedent annotations and associated with like 6K mentions. So this is a recall of like the 92%, nearly 92% of the gold split antecedent anaphoras, but with a lot of false positives. But we have like the manually examined the some of those examples, the false positive examples, and we found that they are mostly like the two arrows. So the first one is some of those people annotate the singleton antecedent reference chains as a split antecedent anaphora, and then some annotated also the bridging references as a split antecedent anaphora, which is now needed to be annotated in the PD corpus. And for our third corpus, so we use the element of bridging reference from the raw corpus. So this is based on the observation that the individual link between the individual antecedent and the split antecedent anaphora is actually an element of inverse relationships. So we use those bridging relationships as our additional auxiliary corpus in order to improve the performance. And in total, we find just above like 1,000 examples for this kind of bridging references. And our last auxiliary corpus is created from the singleton single antecedent reference. So which we have the richest examples. We have like more than 30K examples of this kind. And beyond the different auxiliary corpus, we also examined like the 3 different training strategies. So we train our system like on the simplified version of the Leotard 2018 system, and then replace the BERT, replace the Elmer embeddings with the BERT embeddings. So we only use the reference part of the system because we use gold mentions. So we do not need to we do not need to detect to do the mention detection part of the system. And in terms of how to combine the auxiliary corpus and our main corpus, we have 3 different strategies. So the first and the simplest strategy is simply concatenate them, and with 50% of the time training on the auxiliary corpus and 50% of the time training on the main corpus. Our second strategy is called pre-training, sometimes also known as the fine-tuning approach. So basically, we train the first on the auxiliary corpus, and after the training, we train on the main corpus purely. But this kind of approach is it's shifted very dramatically when you just simply after the training, and then you directly switch to the to different corpus. So we, in addition, we introduced like our third Anino method, which is a smooth version of the pre-training. So basically, we progressively decrease the use of the auxiliary corpus, and in the end of the in the end of the training, we were 100% training on the main corpus. So it's more smooth, and we will show that it's actually quite helpful for some of the of our experiments. So in terms of the evaluation metrics, we use 2 different metrics, the linear score and the strict accuracy. So for the linear scores, we use the similar measures as Valata proposed by the Valata, and which means it gives like the partial credit for the split antecedent anaphoras. Such as the example here, we have the Anaphora all 3 colors. So the antecedent for the all 3 colors is actually a green, blue, and black. So and as we can see here, the predictions is only captured the green and blue. So in a linear evaluation, which will give 2/3 of the recall and 100% precision, and give us a F1 score of 80%. But in a strict evaluation, so we will give 0 scores for these examples. For the strict evaluation, we only give credit to the predictions only if it gets every the antecedent correctly. So which means in here only if the predictions is green, blue, and black, then it will give like a scores for that. So we first we're trying to say which training strategies is the best for each individual auxiliary corpus. As we can say, we first tested on the baselines, which only uses our main corpus, trained on this solely on the main corpus. That is already achieved quite reasonably good linear scores, which is 58.2. But by using like the different auxiliary corpus, we can further improve the performance by up to like 11 percentage point, which is using the Anino method for the single antecedent coreference. And also the element of bridging reference also achieved quite good results by using the pre-training as well as PT crowd as well. And then for the PT silver, the simple concatenation works best. So in the we tested our method with the best training strategies on the test set. So basically, as we can see here, we also introduced some additional naive baselines, additional to our neural baselines. So as we can see, we choose like those recent settings is basically we choose the most recent entities as a split antecedent of the split antecedent anaphora. So by using from two split antecedent up to 5 most recent entities, as we can say, it achieved some lenient scores, but in terms of the, the strict accuracies, so it's a little bit covered up. So let's see, we'll put here. And then, so if we have strict accuracies, so it's nearly just a 0 for all the naive baselines. Also, we include a random baseline as well, which means randomly choose like some of the randomly choose the antecedent. And whereas our neural baselines achieved much better lenient scores, as well as it achieved some stricter accuracy scores of 22.7. And by using our auxiliary couples, we can further improve the performance by quite large margins, which is by again 11 percentage point on the lenient scores. And then for the strict accuracies, it's like 20% improvement. We also try to combine those different settings as well. So by using together the PD crowd and element of and the single antecedent reference, we can further improve the performance by slightly on the lenient score, but by 1 percentage point on the strict accuracies. So after that, we also did some analysis on our we also did some analysis. So first we compare our neural baselines and our bias modules on the split antecedent Anaphora with a different number of split antecedent. So vast majorities of the split antecedent Anaphoras has like two antecedent, and then a small portion of them has 3 and more antecedent. As we can see here, in both cases, our best modules outperform the neural baselines by quite large margins, but a larger improvement is should on the split antecedent Anaphoras with 3 or more antecedent. And another thing we notice is that so the single antecedent reference, it's actually have way more examples when compared to all the other auxiliary couples. So we trying to understand the effectiveness of each individual types of the couples, and by using the similar sized single antecedent and single antecedent Anaphoras. So the first things we did is 1K, use 1K of them, which is equivalent to the Bridgen, and the result shows that it's lower than the Bridgen. So the Bridgen has like 64 lenient scores, which is better than the single antecedent reference. And then we use like the 6K, which is a similar size than or the PT crowd, and the system achieved a similar result than the PT crowd. And after that, if we increase the number of the split antecedent Anaphoras, and the performance keep increasing until we use all of them. So which basically means if we have like the more data, and then it improves slightly more and slightly more in terms of the performance. We also did some like the show some like the examples from our system and the baselines. As we can say, both the false negative and the false positive has been largely decreased by our bias modules when compared to the neural baselines. And so that comes to our last paper, which is our works on the Bridgen reference resolution. So this is in collaboration with Massimo. And so the first, let's have a look about the Bridgen reference. So Bridgen reference is different types of the Anaphora reference, which is mainly dealing with associative relationships between the entities. When compared to the coreference, which dealing with the identity relationship, so the bridging, we can have an example here. So as we can say, the example, the Bakersfield supermarket went bankrupt last May. The business closed when its old owners was murdered by the robbers. The murder saddened the customer. So here we can find our preference chairs such as the supermarket, the business, and it. And then we also have the bridging relationships such as customers. It's customers of the supermarket. So this kind of relations. But we have like the few different challenges for the bridging reference. So the first challenge is they have like the different definitions of the bridgings. So majorly we have two. So the first one is the bridging based on the relational nouns, which is called by the referential bridging by the Rusiger. And this kind of the bridging references need to have antecedent in order to be interpretable, such as John worked towards the house, the door was open. So here's the door, it's a house door. So it's kind of like you need an antecedent in order to specify which door it is. And we also have the more general bridgings. It has been called by Rusiger the lexical bridging. And this kind of like the bridging examples, it can be, interpreted by itself, such as the Madrid in the example here. I went to Spain last year. I particularly like Madrid. So Madrid itself, it's already interpretable. So it does not need the Spain to be used as an antecedent in order to interpret it. So where like the different corpus has a different annotation scheme, such as the raw corpus, the IST trends, and also the pairs has both types of the bridging annotated, whereas the ice note, bash, and the science corpus only have the so-called the referential bridging annotated. So this comes to the second challenge. So the bridging corpus is normally quite small in terms of the number of examples. So the largest corpus, the raw IST, only contains around 3K bridging examples, which is much smaller than the reference corpus. Usually contains like tens of thousands examples. And the other corpus, such as the ice note, have even smaller, right? So they only have 600 bridging examples annotated. So by dealing with those two challenges, we introduce a multitask learning-based framework to dealing with those two different challenges. So by using only like the non-corpus specific features, meaning that a neural network, so we can dealing with different corpus naturally. And also by using a multitask learning framework, we can learn we can enhance the performance of the bridging reference by using the reference examples. So by doing that, we can dealing with second challenges, which is the lack of the resource. So basically, our networks, we concatenate three different embeddings: the word embeddings, the contextual independent word embeddings, such as the glove embeddings, and then we also use the character-based embeddings together with the contextual BERT embeddings, concatenate them, put them together with a multi-layer like the bidirectional LSTM, and create the mention embeddings and the mention pair embeddings, and then we have also has options to share some feed-forward neural network layers between the bridging reference and the reference as well. And then in the end, we have a joint classifier to do the classifications for the bridging reference. So the first things we did is we're trying to identify which is the best settings, how many like the layers we need to share in order to achieve the best performance. So we test our systems on the two different corpus on the by using only the bridging coreference. So we did on the IST and the ice note corpus. So for the IST, the system already achieved quite a good result, which is 47.4. And then on the ICE node, because the corpus is much smaller, so the performance is also lower. And then we did some multitask learnings. So by first sharing the embeddings and LSTM layers, which means basically we share here the mention pair embeddings, but without sharing any feed-forward neural network. And by doing this, we've already can largely improve the performance, especially for the ICE node. And we did further sharing like the 1 or 2 feed-forward neural network layers. And we can say the best performance is always achieved by sharing 1 additional feed-forward neural network layers, which is a 7% improvement when compared to the baseline on the IST, and then nearly 10 percentage points when compared to the ICE node baseline. So after we did the antecedent selection task, we also do the full bridging resolution, which means we don't use the gold bridging anaphoras in this evaluation. So which creates like a F1 scores for the full bridging resolution, and as well as a byproduct the anaphora recognition F1 scores as well. So if we we train the systems purely on the bridging corpus, which we achieved like around I mean the 13.8 or 30-ish on the F1 score, and a quite lower recall here. So we did like some multitask learnings, and then we show that it actually can improve the recalls for both like the full bridging and anaphora resolution by quite a large margin, but the recall is still much lower when compared to the positions. So that's why we did some undersamplings in terms of the reference examples. So by remove some like the certain portions of the bridging of the reference examples, we actually improve the recalls for the bridging as well. And so as a result, it achieved overall, it also achieved a better overall result on the F1 scores for both anaphora recognition and the full bridging. So after that, we apply our systems to the to the more corpus and the test set, and compare to the previous work. As we can see here, for the antecedent selection task, our system achieved the state-of-the-art result on 5 out of 6 corpus, and also it's the first system reported results for all the different corpus. And the only exception is on the ICE node or system. It's lower than the Howata systems. And this is mainly because the Howata systems is tailored only for the ICE node. And the performance on the other corpus, such as IST, is much lower. And where our system, our modules is designed for the for using using only the non-corpus specific features. So which means like it works generally well on the different corpus. And again, we did also for the full bridging and anaphora recognition and all different corpus. And as we can see here, our system achieved always the best result when compared to the previous works. So if you are interested in our like the different systems, so the pre-trained modules and our code is available on the 3 different repositories, the GitHub page. So feel free to have a look. And thanks for listening.